Welcome back, Research Design and Analysis students. Today we're going to do a walkthrough for One-Way ANOVA within, which can be used for matched subjects or repeated measures. This goes along with Privateera Chapter 13, if we are using that textbook with you guys this semester. And when we look at this information today, we're going to keep in mind our learning outcomes. By the time we get done with this section, we should be able to identify the assumptions for the one-way within subjects ANOVA, define the one-way within subjects ANOVA, and identify the sources of variation that come in the statistical procedure, calculate the degrees of freedom for the one-way within subjects ANOVA and locate the critical values, use the 4 steps of hypothesis testing to run this kind of statistic, compute it with SPSS and a post hoc testing if we need to interpret our results, compute the Bonferroni correction procedure for post hoc, and explain why it's appropriate to use for a significant one-way within subjects ANOVA, and summarize what we found in APA format. So the thing to keep in mind with ANOVA, as with each test we learn, is why we're using this particular statistic. A one-way ANOVA within subjects is for comparing potential differences for 3 or more groups or levels of an independent variable to see how those 3 groups differ on an outcome or dependent variable. So in this case, our independent variable is going to be nominal, or maybe ordinal, that we've kind of put into 3 chunks in order. So this could be something like political party, Democrat, Republican, Libertarian, Green Party. Or it may be something where we've chunked people from a continuous variable into 3 different levels, like maybe youngest students, middle-aged students, oldest students. So we kind of have young, middle, older, and that could be something that's kind of ordinal that we're used to group people. Our dependent variable needs to be continuous, which means interval or ratio data for us to appropriately use in ANOVA. If we wanted to use ordinal data as an outcome, we would need to move to a non-parametric test, and same thing if our outcome was categorical or nominal, we'd need to move to a different test. The primary difference for a within subjects ANOVA, as opposed to a between subjects ANOVA that we were learning about before, is that the participants in a within subjects ANOVA are either repeated, like the same people at 3 different times, or they are matched in some way. So maybe some other important variable has been used to match them, so that each person is matched to someone of the same ethnicity, even though they are in different levels of the independent variable. So our subjects are not completely independent. Again, it's either the same subjects at multiple times, or they've been matched on some characteristics, so they have a little bit related. The assumptions of the one-way F statistic that we calculate to do in ANOVA is that we are using normal sampling distributions, either normal populations or a very large N, so that it can handle data that is not completely normally distributed. That we have homogeneity of variance, so that the shapes of the distributions of data for each of the groups is relatively the same shape. And again, for this test, that we have dependent observations, either a within subjects design across time or some kind of matching on an important characteristic for our participants. And when we look at running in ANOVA today, as we figure out about how to calculate it, and again, for my class, I don't have you hand calculate the statistics. We let SPSS do the calculations for us, but we still need to know what ANOVA is doing on SPSS. All of our inferential hypothesis tests have 4 steps. We're going to state our hypotheses, our null and alternative in both English and math. We're going to define our boundaries by setting an appropriate alpha level, so that we're only having a little bit of risk for type 1 or type 2 error, and we're setting our critical F value. What's that boundary beyond which we would say, yep, that looks kind of interesting or meaningful as far as a difference in the real world. We run and report our tests, both our descriptive and inferential statistics, and then we interpret our results both for a math audience, say the kind of things the statisticians like to see so that they know you know what you're doing, and then try to break it down for a non-math friend, or translate math to English, as I like to say, so that your friend who doesn't know what any of this math stuff about still understands how the concepts are different or not. So when we calculate this F ratio for a one-way ANOVA, keep in mind that our Hypothesis for an ANOVA is always directional. It's always one-tailed. We are trying to figure out if the difference in the first group, if the score for the first group is on average the same as the second group and the same as however many other groups we have. So whether those means for each of those groups, represented by the Greek letter mu here, are the same. This is our null hypothesis. And our alternative hypothesis is always that there's a difference somewhere. Now, some textbooks use the symbol for standard error squared here to look at variability. So we could also say it is the variability across the groups the same, or is the variability different. Some other authors prefer to use the means. However you look at it, keep in mind this F statistic for an ANOVA is looking for differences in the outcome across groups or levels of that independent variable. The logic for a one-way ANOVA within is going to be the same for a between subjects ANOVA, except that we should have smaller error variance. So there should be no difference across subjects or participants, either because it's the same people or we've matched them on something important, so that we have less unsystematic variance in the data, and we can get focused in a little bit more on the influence of the independent variable or predictor variable that we picked in its relationship to the outcome. So I'm going to talk to you a little bit about computations, even though we're not doing stuff by hand. One way to keep in mind what that F statistic, which is what we have for an ANOVA, is doing, is it's seeing whether the variability that happens between groups or across groups is stronger than the variability that happens across the whole group of people. So there's a couple ways you could say this to help you understand what an ANOVA is doing. We're looking for the difference in values across groups and seeing whether that is bigger than the difference between persons and within groups. We could also say the difference in group means is bigger than the difference between persons or within groups. Or you could say the variability across group means is different or bigger than the variability between persons and groups. In other words, if the variation in mean scores between groups is larger than the variation within groups or between persons, we will reject our null hypothesis and support the research hypothesis, which suggests that there is a difference across these groups of the independent variable on the dependent variable we're studying. Now, the last thing that we're going to take a look at before skipping a few slides on the math, but you could pause your video to look at those if you'd like, is how to calculate the degrees of freedom. The degrees of freedom is the number of scores that can vary in a particular group, and we'd still come up with the same average or outcome. It's kind of like musical chairs. Everybody else gets to pick a seat until the last person, so how many people get stuck with the score they were given? So in a between subjects ANOVA, the degrees of freedom is a little bit different than the ones we need for within subjects. We still will be considering overall the total degrees of freedom, which is going to be equal to n minus 1. But here, n is the total number of scores, not participants, because the participants repeat. We will look up our critical value in our table by taking the degrees of freedom for subjects. This is n minus 1. And the degrees of freedom between groups, this is k minus 1. And to make our error part that we need to look up stuff in the back of our book, our bottom part, or our denominator, is going to be the multiplied part of our degrees of freedom between subjects, n minus 1, times our degrees of freedom between groups. This is k minus 1, where k is the number of groups. So this is what goes in the denominator, which was a little bit different than our between subjects design where we had n minus k. Our degrees of freedom for our numerator is going to be k minus 1, that's the between part, and then this is the part that we have left over to wrestle with that will go in the denominator. So if we are looking at SPSS, we're going to get a table that looks kind of like this. And we are going to focus in on the variation that we get between the groups and then divide that by the variation that's left over to see if there's a difference. All right, so between and error are the two places we'll look at our tables. Okay, fill this in a little bit with some sample data. All right, and again, you can pause here if you'd like to do more of the hand calculations, or you'll need to use other resources if you're in a class that's having you do that. But when we try to figure out where is our critical value, where's that F value cutoff that tells us, yes, a difference seems to be present, again, our numerator degrees of freedom are going to be k minus 1, where k is the number of groups, and that's here across the top. If you have 3 groups, you would need to do 3 minus 1 is 2 degrees of freedom, etc., etc. So this is how many groups, minus 1. And then our degrees of freedom in our denominator is going to be n minus 1 times k minus 1. And that's what we're looking at in green here down the side. When we see where these two numbers line up, we can figure out what our critical value is. So usually in tables, the light number is an alpha level of 0.05. The darker number is an alpha level of 0.01. So in this particular case, if we had 4 degrees of freedom in the numerator, 18 in the denominator, this here, 2.93, would be our critical value for an alpha level of 0.05. All right, or if we had a larger degrees of freedom in the denominator, we would drop down and look at a different F value, okay, etc. So we're going to be looking at, again, numerator and denominator to figure out what's that cutoff value that tells us whether something is significant or not. Now, if you're interested in calculations, all right, I will slowly go through here, and you can use these slides to help figure out what are those pieces of variability that you need to help do your math calculations. Again, you can pause anywhere you'd like if you're trying to figure out how we're getting to that ratio that we need, which compares the variability between or across groups versus the leftover variability across everybody. And the last couple minutes here I want to take to do an example. So if we were doing a within subjects ANOVA where we wanted to see which chips people liked better, and it makes it within because the same people are eating all 3 kinds of chips and rating them based on flavor, here is what step 1 would look like. We would still state our hypotheses, with the idea that perhaps some nacho chips taste better than others. This is our alternative or research hypothesis that shows us the mean flavor rating across those 3 groups are not equal, or there might be a difference somewhere. We are testing mathematically our null hypothesis that suggests all of the chips taste about the same. And again, same people eating all 3 kinds of chips and rating which one is most flavorful. In our second step, we would state our boundaries. If we were using an alpha level of 0.05, we would go to our table in the back of the book. If we've got 3 kinds of chips, that's k equals 3 groups. We take 3 minus 1 to get 2 degrees of freedom for our numerator. And our error is going to be the number of data points that we have minus 1. So that would be 23 minus 1, or 22. And when we multiply that out, we would get 44 degrees of freedom. So we can use the table in the back of our book to locate that critical F value that tells us where's the cutoff in this distribution that we need, that if we're past it, we've got something that looks interesting or different. When we run our data in SPSS, we will need to calculate and report the means and standard deviations that we get, the standard errors. So we would put those down into a nice APA format table. This is updated for APA 7th edition. And then we would need to go to the within subjects effects to look at our within subjects ANOVA to figure out with our 2 parts of degrees of freedom, is this F value big enough in order to be significant or unlikely? If you run this in general linear model instead of one-way ANOVA, you will be able to do this repeated part, and it will also give you the partial eta squared or effect size so you can figure out how big a difference we have. Right. Once we get that data, we can write up in a sentence whether we have something meaningful. So here's a way to show you that. And you can put it in a graph.